Hi, welcome. Welcome to your lesson on reciprocal functions. Great topic. Let's jump in. It's fantastic. First of all, let's begin with what is a reciprocal? Here's an example of a reciprocal. Here's a number. If you take that number and write 1 over that number, we get what is called a reciprocal. Here's another example of a reciprocal. We had a fraction that began as 3/4. The reciprocal of that is 4/3. You just flip the fraction over. In terms of a general rule for reciprocals, if we have a number and we multiply by its reciprocal, see how this looks like this, we always get the answer 1. That's how you know you have a reciprocal. For example, 5 times 1/5 is 1. 3/4 times 4/3 is 1, because you would have 12 over 12, which is 1. So that's the rule. That's how you know you have a reciprocal. Let's try that rule here. We have a fraction, 1/2. Its reciprocal, 2 over 1. Also have 5/6, and the reciprocal 6/5, or negative 17/3, and reciprocal negative 3 over 17. Let's check if the rule works. So you multiply each one by the reciprocal, you should get 1. Let's try here. 1/2 times 2 over 1 definitely equals 1. 5/6 times 6/5 definitely equals 1. Negative 17 over 3 times negative 3 over 17 also definitely equals 1. Those are reciprocals. So let's talk about the reciprocal function. It's a function that comes from the idea of a reciprocal. It looks like this. F of x equals k over x, where k is some non-zero constant. So imagine some number here that is not 0. The reciprocal function in simple form, the simplest form, looks like this. Y equals 1 over x. So in this case, our k value is 1. So notice this 1 over x is a reciprocal, like we've been talking about. It's the reciprocal of x. So let's investigate this function a little bit more. Basically, you're going to see something like this. We're going to graph a reciprocal function. We're going to notice there's going to be two curves, and there's going to be these kind of gaps between the curves, which are called asymptotes. We'll talk about those a little bit more in our investigation. But basically, on this graph that we see here, we can see that the graphs are approaching these dotted lines, which are not actually part of the graph. We draw them in later to show that the graph itself is approaching these kind of invisible walls and never getting there. And that's happening in every direction here. So we have a vertical asymptote here, horizontal asymptote here. Let's talk about that some more. First of all, the word asymptote is derived from the Greek asymptotos, which means not falling together. Okay, so here is the investigation we're going to do. Grab your notebook and your calculator, or maybe you actually don't need your calculator for this. Let's try it out. Here's our basic rational or reciprocal function, and we are going to fill these tables of values and then graph it. So first of all, put x equals 0.1 in here and see what you get. So 1 divided by 0.1. Well, hopefully you got 10, or you're thinking 10. How about when x is 0.2? Well, in that case, 1 divided by 0.2, there's 5 0.2's in 1, so 5, and keep on going, fill this in. Alright, let's check your numbers. We have that. So notice x becomes small and y is big, but as x grows, y becomes smaller, so they kind of do the opposite of each other. Okay, how about on the negative side? Let's say you go negative 0.1, negative point. Well, you should notice that these are going to be same values, but with negative values. So once you have those values, in your notebook, on graph paper hopefully, let's plot those points and then connect the points and see what it looks like. See what this graph will look like. Okay, so if you plotted it, there's your first point, 0.1 and 10, and then what was the next one? 0.2 and 5, and so on and so on. You have to be pretty careful, but hopefully you got a graph that looks something like that. You can connect it with a curve. And on the negative side, you should have gotten these points. Okay. So connect those. So you have now what's called the basic reciprocal curve or reciprocal function. It looks something like, oh, let's go. It looks like that, right? Connect those points. So that's our basic function. Here I have it graphs and decimals. So you can see there's the curve on that side, the curve on this side. Okay, let's talk about some more details of this. So back to here, our first question, we're going to have 4 reflection questions here. First ones are going to begin with describing what is called end behavior. It means what is happening to a function at the ends of the function, at its extremes. So for example, as x values get larger and larger, so we're going to the extreme of the x values on the positive end. So as x values get larger and larger, approaching infinity, what happens to the y values? So let's take a look at this. As x values become larger and larger going this way, what's happening to our value of y? What's going on? What's the end behavior there? Okay, maybe you wrote something like this. So what I have is as x values get larger, the end behavior of the graph is that y values get closer and closer to 0, but they never reach 0. You may have noticed our values in our table that, let's go back to the table. Oh no, so many things. All right, x values get large, but these ones will keep becoming smaller, smaller decimals, but they'll never get to 0. Okay, next question. As x values get smaller and smaller, approaching negative infinity, well, that's a strange thing to do, approaching negative infinity, what happens to the y values? So in this case, we're going this direction, x values becoming smaller, smaller, going towards negative infinity. What happens to the y values there? What is the end behavior of the graph on that side? All right. As x values get smaller, the end behavior of the graph is that the y values get closer and closer to 0. The same as here, but they're getting closer and closer to 0 from the negative side of y, whereas here they're getting closer to 0 from the positive side of y. And they don't reach 0 as well. Okay, question C here. What happens as x values approach 0 from both positive and the negative side? So now, and then what is the y value when x equals 0? So now we're saying what happens when x values approach 0 from this side and this side? What is happening to y? Okay, the answer there is as x values approach 0, the y values approach infinity, both positive and negative infinity. Okay, let's take a look at that. So as x approaches from this side, you can see y jumps up higher, 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 it goes to infinity. And then on this side, it approaches negative infinity as x gets closer to here. Okay, and also, what is the y value when x equals 0? Well, when x equals 0, it's not going to work out. Why? What's the equation of this graph? If x was 0, we would have 1 over 0. And that is an undefined thing in mathematics. So that tells you that this graph cannot exist when x equals 0. That's a big hint as to where the asymptote will be. Finally, based on your reflections for A to C, add the sketch of the horizontal and vertical asymptotes. So that's what we can do now. Think about where the holes in the graph are. What are the things that the graph is approaching but never getting to? Okay, so here's our function. And we know now that there's an asymptote here because we just learned that x cannot be 0. If we put 0 in here, this would be undefined. So this graph does not exist. There's like a hole in the graph there. And that's what you can see the graph doing. It's getting closer to 0. It wants to get to 0, but x cannot be 0. So there ends up being what's called this asymptote, an invisible wall that this will never reach from either side. X equals 0. And that's a vertical asymptote. There's also a horizontal asymptote at y equals 0. Because we saw for the end behavior as x became big, the graph was approaching 0 but also never reaching it. And this way also, it was approaching 0 but never reaching it. Okay, that's an important concept. That's why we spent some time on it. Those are asymptotes, and that is a reciprocal function. The domain is this. X is an element of the real numbers. It means x can be any real number except x cannot be 0. What would be the range? Well, the range is just like the domain. Y can be any real number except it cannot be 0. This is another way of writing that. Okay, let's do another last thing here. We're going to start using some calculus language here because soon we'll be doing calculus. So here's our function, the limits. We're going to talk about what a limit is. A limit is what happens to a graph when you take it to its limit. So here we have the limit as x approaches infinity. That means as x goes this way, x is approaching infinity. That's what the arrow means. Then the function, f of x, that means the y value approaches what value? Well, 0. We talked about that. As x goes this way, the y values approach 0. And now, as x approaches negative infinity, that means as x is going this way, what does the function, what does the y approach? Also 0. Is now, as x approaches 0 from the positive side, x approaching 0 this way from the positive side, what's happening to y? Y is approaching infinity. And now, finally, as x is approaching 0 from the negative side, x is approaching 0 from the negative side, what is happening to y approaching negative infinity. Very important concepts. We'll look at that soon again when we do calculus. And adding asymptotes, we have one there and one there. Great. Let's look at a couple more things. Okay, here's a reciprocal function, here's another one, here's another one. Hey, they all look kind of similar, but this is the graph of 1 over x, 2 over x, and 3 over x. 1 over x is the one we were just looking at. 2 over x, if you can see it, there's a subtle change. Basically, these curves have moved away from the center a little bit more. And here, with 3 over x, they moved even further from the center. But they all have the same shape, they're all reciprocal. One important quality, if a reciprocal function looks like this, then we can rearrange that, multiply by x, and we get xy equals k. What that means is any x and y coordinate on the graph, you can multiply to get the k value, which is this one here. Let's take a look at that in detail on Desmos. So here I have a reciprocal function, our basic one, 1 over x. Now I'm going to plot a point on it. There's a point right there. That point is 0.254. What happens when you multiply x and y? X times y, 4 times 0.25 is 1. And notice 1 is our k value, the top value there. So again, going back to here, when we multiply our coordinates, we'll always get that top number in the function. Let's try that with the second one. Y equals 2 to the x, or sorry, 2 over x. Here's the second reciprocal function. Here's a point on it. 1, 2 is a point on that graph right here. And what happens when you multiply x and y there? 1 times 2 gives you 2, which means we're getting the top number in the reciprocal function. Let's try it for y equals 3 over x. This red one is y equals 3 over x. So I picked a point, 3, 1. Let me label that one as well. Here's 3, 1. What happens when you do 3 times 1? 3 times 1 is 3, gives us the top number. So any point on the graph, if you took any point and multiplied those two numbers, for example, let me go here also, let me go a little further. 5 and what is it? 5 times 0.6 also gives 3, that top number. Any point on here, you'd multiply x and y, you'll get the top number. Okay, great. Okay, please pause and read this problem, and then fill in some values in this table. In this table, you'll try and fill in length and width numbers for this parking lot. That will give an area of 800. Okay, let's check. Here are some options. Length is 1, width is 800. Multiplied, that makes an area of 800. 5 times 160, that also multiplies to make an area of 800. 10 times 80 also makes an area of 800, and so on and so on. Hopefully these match some of the ones you listed. Okay, the point is that any combination of length and width here, you multiply them to make 800. That tells us when you multiply x and y, well, we just learned that means this is going to be a reciprocal function. So what would be the reciprocal function for this area of this parking lot? It would be this, right? We begin with the constant equals y times x. We found out that y times x in this situation must be 800 every time to make 800 area. Solve that for y, and we have this reciprocal function representing the relationship between length and width with the area that has to be 800. Okay, let's take that a little further. So we know that length is y, width is x, and now read this condition and see if you can write an equation to represent that condition. Okay, we have our original function for the area, and now we learn that length must be twice the width, so I can write this second function. And now, new question, determine what the length and width of the car park will need to be. We have two conditions on the car park. It must meet this model and this one. It must be 800 for the area, and the length must also be twice the width. So how can you solve this? Well, we can set them equal to each other because we're trying to see when the car park meets both conditions. So setting them equal to each other, using your calculator, graphing, find the point of intersection. All right, here's a graph. You might have to change your window a lot. There's that reciprocal function. Here's the line from here. Where they intersect is right here, and that shows me the point 20, 40. And that point of intersection meets both conditions. That means this is twice this, which we can see meeting that condition, and also 20 times 40 makes 800. So we found out what the car park must be. Try one more. Read this out. See if you can make the reciprocal function, and then answer the questions. Try it all out. Give it a good try. Okay, check your table. Check your function, like that. Then check this condition, which is there must be 50 photos, so that's y equals 50. And finally, there's a graph and a solution, and also solved algebraically just by setting them equal to each other. Great job!